Welcome to another video on smart architectural programming. And today we're going to be focusing on solving another blind 75 problem, and it would be the first of the binary tree related problems, particularly the binary tree problem. So in this problem we need to invert a binary tree, as you can see on the screen right now. So ultimately we need to first understand exactly what we need to do with this particular problem, right? So our problem is that we're given a root of a binary tree and we need to invert the binary tree and return its root. So given a root with associated branches of that tree, we need to invert that tree with the given root and then return that to back basically. So generally speaking, it would look something like this, as you can see the input and output here. You put in the input like this, you get an output like that basically. But it seems nonsensical to a degree to understand a tree problem using just this data. Rather, it would be difficult to visualize and ultimately implement such a problem if you don't understand exactly what's happening. So let's focus on exactly what happens in this particular problem. So we're given I picked this up from the internet here. So we're given a particular tree here, right? We are given a tree here, right? Given this tree, how do we how would an inversion look like basically, and that would help us actually visualize what we need to do. So let's use one color here to depict different layers. So we have one layer here. This was a little bit out of the, let me try to use another tool here, if I can stretch a line tool here. Yeah, so given this, give me a second. Let me again use the pencil tool. It seems the best thing to use is that pencil tool, as long as I'm careful with how I draw the line. So given this tool here, this is the first layer we have, right? And divide every node layer of this binary tree basically to visualize this problem. So every stage where the nodes divide into a further branch, that's one layer, and given that presumption, we're going to divide this into different layers basically. So the second layer is in the second different color. So this is the second layer, and the third layer should be in a different color as well. We'll just use sea green for that. And every line is depicting the layer, the nodes above this. This line is representing the nodes here, this one here, and this one here basically, right? So given that that we understand exactly how these nodes are working, we first need to understand what these different nodes are. So in the first line, we just have one node, right? So honestly, if we just use common sense here, no inversion could occur in node number 1, right? And this is the root node. The root node is the node that is in the top of the tree. So this is the root node. Based on that, we can presume quite effectively that the root node cannot be inverted because there is nothing else to invert it with. So we need to do nothing on the root node basically. No action needs to take place on the root node basically, right? So given that, let's move on to the second node, which is in the magenta color. So in this particular node, what you'll notice here is that we have two nodes here in this layer, but it's a little bit tricky. This layer isn't that tricky. So we just have two nodes here. So what we need to do simply is to interchange the positions of these two nodes. And we'll explain exactly how this would work in the next node. There's a certain layer of complexity to the inversion here, because let me actually just explain that here. Because we're not just inverting 2 and 3 with each other, as you can see here. 2 moved to this position here, right? And 3 moved to, let me just use a different color to depict these things. It becomes a little bit messy with the same color. So 2 moves to this position where 3 was previously, and 3 moves to 3 moves to a different position. It moves to the position where 2 was previously, right? that is not just what is happening here. Notice something else in the inversion tree. You'll see that the inversion is also happening in the entire child nodes of this particular tree. So this tree moves to the other side, but the entire child nodes of this node also move here. So 3 has 6 and 7 with it, right? But along with that, 7 and 6 also move there. So we need to move the entire node. The entire child node needs to be moved from one place to the other, basically. So that is basically the trick of this question. You need to understand that every node must be inverted along with its child nodes, right? So similarly, what happened here, let's use the same color here. So if you notice this node, 4 and 5 moved with it and inverted with it as well. So that is how these two particular inversion work in this particular layer. So let's remove all of this, considering we need to keep the layer a little bit cleaner to understand the next step. Given that, let's move on to the layer number 3. So what you'll notice in the layer number 3 is that we have 4 nodes here. But keep in mind, child nodes only interchange with each other, right? So we moved the entire child nodes along with 2 and 3, right, in the previous layer. So in this layer, basically there are 2 sets of interchangement, not 4. We won't change all 4 brackets. Just keep in mind, interchanging only works with 2 values, right? 2 values can only interchange with each other. In this particular question, just visualize that no more than 2 nodes can interchange with each other, right? So 4 and 5 interchange with each other, and 6 and 7 interchange with each other, and you'll notice that happening there, although their positions are changed. So 3 moved to 2 sides, so we have 6 and 7 here, but 7 and 6 interchange. 6 was before 7, but now 7 is before 6. That's how what happened here. As you can see, let me just use a color to depict that. So you notice that 6 moved from the right to the left, and 7 moved from the left to the right. So this is what happened with this particular problem, and that is what happened in the other node as well. So this is the basic inversion problem that you need to solve. Logically, that is what is happening to solve this inversion of binary tree. Given that, let's move on to the problem itself. And to a degree, I'm not going to focus on solving this problem. This value here is just they're giving us a definition of the binary tree node and how it's defined, right? And the class, how the class is defined. So I've already solved this problem. The reason I'm not coding it out in front of you, because it didn't make sense to do that. It's better that I did that previously. It makes more sense that if I explain the code that is already there instead of typing it out. That doesn't make sense. That doesn't create value for your time. So let's focus on exactly what we're doing in this code here. So as you can see on line 10 here, we have a base case because we're doing a recursive call. Not so of a recursive call, I think, but more so what we're trying to do here is dealing with an extreme case. If there's no root node, if we are given no tree to invert, then we also need a response. We're dealing with an edge case. We need to deal with edge cases in our code, otherwise our code would break if an edge case pops up. So in this case, we see that if there's no root node in the given root tree to us, we just return the value none because there was no value given to us. Similarly, rather I think we are using recursion in this particular problem here. So you see we have a base case to exit, right? Not only to exit if there's no value given to us, but to exit out of a recursive call, we always need a base case, a case that finally gets us out of the recursive call, right? Then we have the recursive inverting call. Basically here we recursively invert the left and right subtrees. And as you can see on line 15 and 16, we recursively call the same function that we have defined here, and then we saw at the end we have a logic that runs in the recursive call. So recursive call has 3 case situations: base case to exit out of the recursive calls, recursive calls. Second section is where you do your recursive calls, and the third section is where you basically run your coding logic. So here the third point is where we're swapping the left and right values with each other, right? And then we return the root value. So before I run this code, let me give a little bit explanation here. So potentially we're given this particular problem here. Let me remove all of these drawings if I can, so I can make it a little more clear, right? So first recursive call is this entire value or tree here, right? This is the entire tree that we have given in the recursive call. So how do we solve this? So given this goes into recursive call, the values are we have more than one value here. So if there's if you go back to the code here, you'll see that the base case is no root value. So there is a root value, which means move next, right? Next line. So then we go to the self.invert. We call left invert. We do the left inversion and the right inversion, because there are going to be two parts in the tree, basically, right? So given those two parts in the tree, you'll notice these are the two parts in the first recursive call, right? This one, and let me use another color here. Not magenta, let's use something a little bit easily differentiable. So let's use cyan here, right? So these are the two recursive calls. One is the left call, other the right. The cyan one is the right call, and the purple one is the left call. So given these two calls here, this is the first recursive call will happen, right? So this section would be recursively called by the left recursive call that we did, and this would be the right assigned color would be recursively called by the right recursive call we did. And these nodes here, this node would become the new root node of the new recursive call, and this would become the root node of the next other recursive call, right? This one here, right? Similarly, once this recursive call goes through, we got these two subtrees left and right are going to go to this recursive call. Then within that recursive call, again we break them into left and right. So these two also become broken down into left and right? And after these, another recursive call is done, but there's no subchild elements to that. So there's no recursive call. No root node is sent through a recursive call. So that ends our recursive calls. So then our recursive calls starts to solve these problems. Our logic is inversion. So we invert these first, right? Then we invert these two between each other, and then we return to 1 here, and we have solved our problem, and this output is given through our recursive function, basically. So that is basically how this problem is working. Let's run this code here. All three cases have been correctly solved. Let's submit the code here. It should clear as well. And that is how you solve the inversion of binary tree problem on blind 75 problems. And this is one of the most common interview questions that you'll pop up with. So, prepare this, because there's a sequence of different problems with binary trees. You need to understand how to visualize these problems in order to solve these problems. Given that we understand that, please like and subscribe if you got any value from this video, and let us know in the comments if you have any questions, queries, or any topics that you want us to cover in our videos. With that, I'm going to sign off, and we'll see you in our next video. Thank you.